Modern AI systems all face the same hidden question. Where should context live? In the model, in retrieved data, in training, or somewhere else? In this module, we'll build practical intuition for choosing ML, LLMs, RAG, fine-tuning, or the right mix. We'll move step by step. First, we'll ground the core concepts. Then we'll look at RAG and fine-tuning as two different ways to solve context problems. Finally, we'll turn those ideas into a practical decision framework. The learning path builds in layers: how models learn, how LLMs use prompts and context, and how those ideas shape real architecture choices. With that foundation, RAG and fine-tuning become practical options, not just buzzwords. Use this course based on where you are today. If you're new, go in order and give the foundations time to settle. If you're intermediate, focus on RAG, fine-tuning, and trade-offs, and loop back when a term feels unclear. If you're advanced, treat the lessons as a reference for architecture decisions. Whatever your level, stay active. Pause, summarize, sketch the system, and connect each idea to a feature you could build. Traditional machine learning usually starts with structured features and labels. We train a model to map those inputs to a specific prediction, and much of its knowledge is fixed after training. LLMs work differently. They process tokens, use massive learned parameters, and respond to prompts by drawing on patterns from broad training. Their useful behavior depends heavily on context, and that context question leads us toward RAG and fine-tuning. Classical machine learning starts with examples. Each example has features, the measurable signals, and usually a label, which is the answer we want the system to learn. For email, features might include length, suspicious links, or sender reputation, while the label is spam or not spam. Training adjusts the model to connect feature patterns with labels. Validation checks whether those patterns still work on fresh data before we trust the model in practice. In practice, classical machine learning is an engineering pipeline, not a magic button. First, define exactly what you want to predict. Then collect and clean data, and turn raw inputs into features the algorithm can use. After training, evaluate with metrics such as accuracy, precision, recall, or error, depending on the task. Once deployed, the system still needs monitoring, because changing data can require retraining. This is why representation matters so much. In traditional machine learning, context usually has to be translated before the model can use it. Engineers take the messy world, documents, user details, past activity, and other signals, and compress it into a fixed feature vector. That vector becomes the model's reality. If an important clue was not captured during feature design, the model cannot reason from it later. Adding new knowledge often means changing features, collecting new data, or retraining. Early machine learning relied heavily on people deciding what mattered: edges in an image, keywords in text, or signal patterns in audio. Deep learning shifts much of that representation work into the model itself. Layer by layer, neural networks learn useful representations, often as embeddings, numerical vectors that capture meaning. With enough data and compute, this made models far more flexible and powerful. Transformers made today's LLMs possible by giving text a structure the model can compute with. Words are split into tokens and converted into embeddings, which are numeric representations of meaning and context. Attention then lets each token look across the sequence and decide which other tokens matter most. That is why cat can connect to sat and mat. Stack many attention layers, scale the data and compute, and you get powerful next token prediction. A large language model is not a fact table with answers stored in rows. It is a neural network trained on huge collections of text to predict what token should come next. During training, patterns become encoded in parameters, the model's internal learned values. That gives the model broad abilities with language, code, and reasoning. But its output is still probabilistic, so knowledge can be outdated, approximate, or unsupported unless grounded with sources. Training and inference are different moments in the model's life. During training, the system studies massive text examples, predicts tokens, measures errors, and updates its parameters. That is where lasting learning happens. During inference, those parameters are fixed. Your prompt adds temporary context, and the model uses both the prompt and its parameters to generate the next token, then the next, until an answer forms. It is generating, not pulling a stored response. The context window is the model's temporary workspace. At answer time, the model can use only what fits there: your instructions, the current question, prior conversation, and any retrieved snippets. Those pieces compete for limited room. If the critical fact is missing, the model does not magically know it for this task. It may infer, guess, or hallucinate. RAG helps by selecting useful external information and placing it into that workspace. Traditional ML and LLMs are different tools, not a simple replacement story. Traditional ML is strongest when inputs are structured and the goal is prediction, scoring, classification, or forecasting. LLMs are strongest when the work centers on language, explaining, summarizing, coding, or conversation. The trade-off is how you steer them. Classical models need features and training data. LLMs need prompts, context, and grounding. Both still need freshness and personalization designed in. You've now built the foundation. Traditional ML depends on features and labels, deep learning learns richer representations, and LLMs combine learned parameters with prompt context. That difference explains why context becomes so important, and why techniques like RAG and fine-tuning matter. Next, we'll sharpen what context really means.